Any questions for me? Good. So today I want to talk a little bit about infinite probability spaces. So if you rewind a little bit, when we started talking about probability, we gave basically a couple of basic definitions, but one of them is a probability space. So for us, that's always been the set S of all the outcomes that we're talking about. And if you remember, the definition was it's a non-empty countable set. So non-empty is kind of self-evident. And countable means that it's either finite or there's a bijection between the elements of the set and the integers. But all the examples we've seen so far, this probability space, the set of outcomes has been finite. So we haven't seen an example yet where there's an infinite number of possible outcomes. So what are examples of such things? Well, it turns out that they're actually easy to come up with. So let's look at the following. We'll toss a coin until the first time it comes up heads. So we'll be talking about this space a lot in this class. So what does this space look like? Well, it's possible that we toss the coin and the first thing that we get is a heads. Then we stop. Or we toss the coin, we get a tails, and then the second coin toss gives us a heads. Or we toss the coin twice, getting tails, and then finally get a heads. Or we toss it 3 times, getting tails, and then finally a heads. Or we toss it 4 times, getting tails, and finally a head. And for any number n, it's possible that we toss the coin n times. Each of those comes up tails, and then finally on the n plus 1th toss, we get a head. And so that means, well, that means that this is an infinite probability space, right? It's an easy experiment to describe, but there's an infinite number of possible outcomes. And I'll use this notation for this as this is the set of strings that look like tails, some number repeated, some number n times, followed by a single head, and that's for any n bigger than or equal to 0. So this is a sort of standard thing when talking about strings. When you take one of the characters and raise it to an exponent, that just means repeat that character n times in this case. Okay. So there's an infinite probability space, or an outcome set. What's the probability function that we should associate with this? So what's the probability, for example, that I toss a coin, and the first time I toss it, it comes up heads? Yeah?
1 over 2.
It'd be 1/2, right? So we've always talked about coin tosses being fair coin tosses. They come up heads or tails with equal probability. So this should have probability 1/2. What's the probability that I toss it the first time and it comes up tails, and the second time I toss it, it comes up heads? Yep. Should be 1 out of 4, right? So again, with coin tosses, when we repeat them, we've always assumed that they're independent. So if you think of the coins being, or the tosses being called C1, C2, C3, and so on, this is really the probability that C1 is equal to tails and C2 is equal to heads. And independence gives us that that's the probability that C1 is equal to tails times the probability that C2 is equal to heads, which is a half times a half, or a quarter. Okay. And so in general, so this one has probability a half, this one has probability a quarter, this one will have probability, yeah, 1/8, and this one 1/16, right? This is the probability that the first one comes up tails, times the probability that the second one comes up tails, times the probability that the third one comes up tails, times the probability that the fourth one comes up heads. So that's 1/2 to the power 4, which is a 16th. And so the probability function looks like this. The probability that I first toss n tails followed by the head is exactly 1/2 to the n plus 1. Right? 1/2 to the n for this sequence of n tails, and then another half for this, this last one coming up head. Okay. That sound reasonable? So now the claim is that S is a, the set S and this probability measure gives a valid probability space. So call this is actually sample set, not probability space. So let's see. All right, so we have a sample set S. It's not finite, but it is countable. I can list its elements out one at a time. In fact, there's an obvious bijection between its element and the integers, its elements and the integers, because really the elements, each one is associated with exactly one integer n here. So that's basically the definition of a countable set. But we got this probability function that we just worked out. And remember, one of the really important things about, well, probability functions, they take elements of our set, map them onto real numbers between 0 and 1, but they'd better sum up to 1. So does this one sum up to 1? Well, if we did it correctly, it should. So let's just check that that's the case. So what I need to know is if I sum up over all the things in S, so the things in S are, I start with n equals 0, I up all the way to infinity. I look at the probability of t to the n h. Right? That's the sum of all of those probabilities. That's the sum n equals 0 to infinity of 1/2 to the n plus 1. And at this point, maybe it helps to write this out longhand. So the first term in this sum is when n equals 0. So we have 1/2 to the 1. The second term is when n equals 1, and then we get 1/2 And then the third term is when n equals 2, and we get 1/2 cubed. So does this equal to 1? What does that even mean? So this thing goes on infinitely like this, and we can convince ourselves actually that this equals 1 with the following heuristic argument, but then we should go back and try to remember what this what it means to even take an infinite sum like this. So we should revisit that, but let's convince ourselves now. So here's I don't know, just a line, a stick whose length is 1. The first term in that sum is 1/2. So there's me drawing the first term in that sum, the 1/2. So that covers half of this, this interval. The second term in the sum is 1/4. So let me tick that off here. There's a length of 1/4. And notice that actually that covers half of what was remaining after the first one. And so what's remaining here is still 1/4. And the next term is 1/8. So if I mark that, that uses up exactly half of what was remaining. And the next one, so what's left here is still 1/8. And the next term is a 16th. And this goes on forever, never quite reaching 1, or we'll see, reaching 1 in the limit. Okay. So this sum here never quite, any finite prefix of this thing never quite adds up to 1, but it gets closer and closer to it, which sounds like the definition of a limit. So this is true, and we'll check that in a second. So this heuristic argument here has a name in the history books. It's called Zeno's paradox. So anybody heard of this before? Yeah. So Zeno was sort of a philosopher, mathematician who liked to ask these paradoxical questions. And his version of this was, well, suppose that somebody wants to run a marathon, then, well, before they can run a marathon, they first have to run a half marathon. And then they still have a half marathon to complete. But before they can complete that, they still have to run a quarter marathon. But before they can complete that, they still have to run, whatever, an eighth of a marathon, and so on. So the quote paradox was that, well, then you can never run a marathon because you always have more left to do, which doesn't, it's not really paradoxical because, yes, everything that I just said is true, but the time it takes you to do each of these things is also decreasing by a half each time. So it still adds up to, a finite amount of time. Okay, but let's remember something. For real numbers, A0, A1, A2, A3, I. So this is a definition. I hope some of you have seen something like this before, like in a calculus class. That's actually equal to a limit as n goes to infinity of the sum I equals 0 to n of ai. Okay. So if this limit exists, then that's the value of that sum, and if the limit doesn't exist, then this sum is undefined. So anybody seen this before? Right. So infinite sums come up, of course, in calculus. And so what is this supposed to mean? Well, when you see something where there's a infinity in the upper bound here, that really means what we're talking about is a sequence of finite sums where each one goes up to larger and larger values of n, and you take the limit of those things. All right? So let's look at one of those things. And in fact, let's look at one that has this form. So what is this thing? This is, for example, here I have A0 is a half, A1 is a quarter, A2 is an eighth, and in general, AI is 1/2 to the I plus 1. So that's an example of this thing here. Those are the sequence of real numbers. So we want to evaluate that infinite sum, so that means we want to evaluate this limit. So let's look and do something even more general. Let's say for x not equal to 1, the sum I equals 0 to n of x is minus x to the n plus 1 over 1 minus x. Okay, so I want to tackle this sum in particular, or sums like it in particular. Here, this thing is really 1/2, looks like roughly 1/2 to the I. So I'll look at sums of that form, I equals 0 to n of something raised to the power I. Okay. All right, good. And so this is the claim. Let's call this a claim. Does anybody know how to prove this? So you can prove it by induction, but there's also a somewhat more clever way to do this. So look at this sum. Well, this is x to the 0. X to the 0 is 1. The second term is x. The third term is x squared, x cubed, x to the n minus 1 plus x to the n. And we're claiming that that's equal to 1 minus x to the n plus 1 over this 1 minus x. But let's just bring the 1 minus x over here. Right? So take this thing and multiply both sides by 1 minus x. That means this one goes away and shows up over on this side. Okay. So this claim is exactly the same as this claim here. But if we look at what's over here on the left-hand side, so forget about this. So this is 1 minus x times this thing. Well, that's just equal to this thing, right? 1 times this thing. So that's the 1 times this thing minus x times this thing. So I've got x times 1 is x x times x is x squared. X times x squared is x cubed, and so on. Right? So minus x times all of this gives me this thing here. And now notice everything cancels out except the first and last term. So plus x up here, minus x down here, plus x squared, plus x cubed, minus x cubed, and so on, all the way to here. And the only thing we're left with is a 1 minus x to the n plus 1, which is exactly the thing we needed to show. Okay, so there's how to evaluate one of these finite sums. So is this clear? I mean, it's clear because we took a wild guess about what the sum was, and then once you have a good guess that's correct, it's usually easy to prove it. So that part's easy once you actually know the answer. And so now, let's say let's take x to be anything between minus 1 and 1, we get this. The sum I equals 0 to infinity of x to the I. Well, we apply this definition. This is just the limit as n goes to infinity of the sum I equals 0 to n of x to the I. This sum, we now know what it's equal to. Right? So we have the limit of a sum. We now have a closed form for that sum. That's what we got from that claim. So we plug that in here. Now as n goes to infinity, what happens to this thing? Well, the stuff on the bottom doesn't change because it doesn't depend on n. And on top there's a 1 that doesn't depend on n. And here I've got an x to the n plus 1. So as n goes to infinity, this is x to a larger and larger exponent. And I've assumed here that x, the absolute value of x, is smaller than 1. So what happens when I take a number that's smaller than 1 and I raise it to larger and larger exponents? Yeah. Yeah, it gets smaller and smaller. Its absolute value gets smaller and smaller. It gets closer and closer to 0, which means the limit of this thing, x to the n plus 1, as n goes to infinity, that thing goes to 0. So we just get 1 over 1 minus x. Okay. So these things are called geometric sums, the ones that go to infinity like this. And there's basically, the only thing that matters is this base here, this value of x. And as long as it's smaller than, its absolute value is smaller than 1, you know exactly what happens here. It's just 1 over 1 minus x. And, okay, does that make sense? All right, so let's then test it. Let's test that out, see if we can use that here rather than using some kind of heuristic argument. So instead of writing things out longhand, this thing here, so I've got a sum going from 0 to infinity. It's something raised to an exponent, but there's an extra plus 1 here. That's easy to take care of, right? This is just sum n equals 0 to infinity of 1/2 to the n times 1/2. That's all that means, right? So this is multiplied. This plus 1 just means take this thing and multiply it by half one more time. Now, this is a sum where I've multiplied every single thing in the sum by 1/2. So I can pull the 1/2 in front of it. Like so. And now, this thing is the sum n equals 0 to infinity of 1/2 to the n. It has exactly this form with x equals 1/2. So that's going to be equal to, let's see what we have, a 1 over 1 minus 1/2. That's a 1/2 times 1 over 1/2. And 1 over 1/2 is just 2, and a half times 2 is 1. So our heuristic reasoning was correct. We get 1 here, and we can get it rigorously this way. Okay. So remember, anytime you see an infinite sum, remember that underlying that, what you're talking about is this definition here. An infinite sum is the limit of finite sums as the number of terms goes to infinity. If you don't remember that and you start playing around with infinite sums, in particular if you start splitting them, then you can run into real problems. You can prove all kinds of things that are not true. Okay. But let's just put this thing aside and remember that for any x between -1 and 1, the sum I equals 0 to infinity, x to the I is a 1 over 1 minus x. Everybody good? And this thing is called a geometric series or geometric sum. Okay, so here's an example of a fun game. Maybe not so much fun, I don't know. Actually, by the end of the class, we'll see a version of this game that's fun enough that you can maybe fool your friends with it. So here's the game. 2 players, P1 and P2, who take turns tossing a coin. Player 1 goes first. So player 1 gets the first turn. And the first player to toss heads wins. Okay? So you and I have a coin. I'll play first. I toss the coin. If it comes up heads, I win. If not, I give you the coin. You toss it. If it comes up heads, you win. If not, you give the coin back to me. I toss it. If it comes up heads, I win. So just back and forth like this. All right. So who would you rather be, player 1 or player 2? So I think we can convince ourselves definitely player 1 has an advantage. So what does an advantage mean? Well, this is purely a game of chance. There's no skill involved. And it's a game of, well, chance meaning randomness. So already, player 1 on the first coin toss wins with probability 1/2. Or maybe he doesn't win at that point, in which case he gives the coin to the other player, player 2, but he still presumably has a chance of winning beyond that. So already you know that his probability of winning is at least 1/2, which means if the game is unfair, at least it's unfair in favor of player 1. So I'd rather be player 1 for sure. But I would like to know, A is the event, player 1, P1 wins. So I'd like to know probability of A. I want to understand this game. Because all these games of chance, they're fun for gambling, and so if you want to know what kind of bets you should accept, when you should play, you should know your chances of winning these games. And knowing probability of A also gives me probability of not A, which is the probability of player 2 winning. All right. So what are these? Well, okay, so I'd like to know that. If we go back and we look at our set S, so this game is really an experiment that's occurring. And the nice thing about it is, so the players take turns tossing a coin. It's only one coin, and the tosses happen one after the other. And the game is over the first time somebody tosses heads. So if we just forget about who's holding the coin at any given time, that means that the sample space, it's exactly the one we've seen here, right? So there's a first coin toss, and possibly, a second coin toss. So it's exactly the same sample space we've seen before, and that's the tails to the n heads for all n bigger than or equal to 0. Okay, and now this event A, where P1 wins, so it includes some of these things. So does A win in this case? Or does P1 win in this case? Yep. He's the first person to toss the coin, and the first coin toss comes up heads. What about in this case? No, that's player 2 who's tossing the coin there. But in this case, this is player 1, player 2, back to player 1, and he wins. And so the set A looks like this, or another way to write that is that's the set tails to the, let's say, n, followed by a head. That's n bigger than or equal to 0, and n is even, right? So an even number of coin tosses come up tails, and then the coin is in player 1's hand, and it comes up heads. And another way to write that, this is awkward here, this condition on the right. Let's just call this, we have some number 2k of tails followed by a heads, and that's for any integer k bigger than or equal to 0. Right? An even number of tails of coin tosses that all come up tails, followed by the winning toss by player 1. All right. Is that clear so far? So now let's look at the probability of A. In uniform spaces, all we need to know is the size of A divided by the size of the space. That's clearly not going to work here, well, because it's not a uniform space. Not all of the probabilities are the same, and dividing by infinity is also not good. It's always going to give us 0. So we have to go back to the definition of what it means. What's the probability of an event like this? That's just the sum over all the outcomes that make that event happen of the probability of that outcome. And what are all the outcomes that make it happen? Well, that's this set here. So I need to sum k integers k from 0 to infinity of the probability of t to k h, which is equal to sum of k equals 0 to infinity. So what's the probability of this thing? So we're looking at 2k plus 1 coin tosses. It came up a very specific way. So that happens with probability. Yep. Yep. 1/2 to the 2k plus 1. Right, we've seen that here. The probability of t to the n followed by an h is 1/2 to the n plus 1. In our case, the n is 2k, so we get that. Again, this plus 1 up here is kind of annoying, but this just means 1/2 to the 2k times 1/2. So we can pull that out and bring it up front. So we get something familiar looking. Okay, almost a geometric series. It almost looks like this, except we've got a sort of 2k up top, and we really only wanted a k to make it look like this. What do we do? Yep.
You rewrite it as 1/4 to the power of k.
Yep. So 1/2 to the 2k is 1/2 squared to the k, and 1/2 squared is 1/4. So it's 1/4 to the k. And so this thing up here is 1/4 to the k. And now we're golden. This is still k running from 0 to infinity. And we're golden here because this looks exactly like this, right? We have summation variable running from 0 to infinity. We have a constant base. In this case, it's x is 1/4. And we're looking at x to the k. So we plug in our formula. That's 1/2 times 1/1 minus x. X is 1/4. So this is 1/2 times 1/3/4 equals 1/2 times 4/3 is equal to 2/3. So, probability of A is 2/3, and A was defined as the event player 1 wins. So if you play this game, you want to be player 1 because player 1 has probability 2/3 of winning, which means player 2 only has probability 1/3 of winning. Okay? That good? So you're twice as likely to win as player 1. So let's save that because we might want to use it later. Well, I want to erase that just yet. So this is what we'll call game 1. And we'll make note here that probability that player 1 wins game 1 is equal to 2/3. Let's consider another game, game 2. Same thing, P1 and P2 take turns tossing a coin. And the winner is the player who tosses the second head. So we play this game. I toss the coin, then you toss the coin. I toss the coin, and you toss the coin until it comes up heads. Game is not over yet. At this point, now we're playing for the real money. We continue to toss the coin until it comes up heads again. Whoever made that toss is the winner. Which player would you rather be in that game? Who knows, right? It's not obvious that player 1 has an advantage anymore, because the way we argued that player 1 had an advantage in this game is we said already player 1 wins half the time on the first toss, but in this case, player 1 can't win on the first toss. Even if the coin comes up heads, then so what? He hasn't won yet. We're still waiting for the second one. So that doesn't seem right. And similarly, I don't see an obvious reason why player 2 has an advantage. So we won't know the answer until we work it out. Yeah?
Why is it obvious that player 2 has an advantage? Because it's like player 1 right away has 50% chance to get first head.
Yeah.
And now player 2 has 50% chance getting, it becomes game one, right?
In the case where you toss the coin, player one tosses the coin heads the first time, then it becomes game one, and agreed in that case, now it's game one, but with player two starting first. But there's that other 50% of the time where it comes up tails, and now it's still game two. And so then we still need to evaluate game two, where now player two is starting first. So it's not immediately obvious to me. We'll see that there is an analysis that works like that, but let's do it the hard way first. Okay. So I don't know, or it wasn't obvious to me at the beginning what the answer would be. So let's say, again, A is going to be the event, P1 wins. And now we're talking about game two. All right. So let's look at this set of possible outcomes, first of all. How does this game play out? It's not the same set as before, because before, all our outcomes involved a sequence of tails followed by exactly one head, and then the game is over. But now the game is not over at the first head. Instead, the game continues after that. So there'll be a sequence of tails, let's say n of those. Then there'll be a head. Then there'll be another sequence of tails, a different number possibly. And then finally the game is over when you see the second head. And this could play out for any n bigger than or equal to 0 and any m bigger than or equal to 0. So the game is over once you've seen that second head, but before the first head you can see any number of tails. Between the first and second head you can see any number of tails. So that's the set of outcomes. All right. Now what about this set A, where player one wins? What does that look like? So, I mean, it's something like and some condition, right? Some subset of this thing, but with some extra additional condition. So what's the additional condition? Yeah.
N must be even, n must be even, and n plus m must also be even.
It's not necessary that n is even. N just determines who tossed the first head. And I don't actually care who tossed the first head, right? That doesn't have anything, that doesn't affect the winner. But n plus m, that is important, right? Because the number of coin tosses that happen before the winning toss is n plus m plus 1, right? And if n plus m plus 1 is an even number, then this is player one who's making this coin toss. So if n plus m plus 1 is an even number, that means n plus m is an odd number. So that's what that set looks like. Okay. And we saw these kinds of awkward restrictions here we don't like so much. But now it's not as obvious how to split them up, right? Because, well, n plus m is odd if n is odd or m is odd, and the other one is even. So we somehow need to break this up a little bit. So let's split it into two sets. So let's call this is going to be A1 union A2, where A1 is P1 tosses the first head and wins, and A2 is P2 tosses the first head, and P1 wins. Right? So if P1 wins, then one of these two things happens, right? Either P1 gets the first head and also the second one, so he wins, or P2 tossed the first head, but P1 got the second one, so P1 wins. So those two things they certainly cover all of A, and of course these two things are also disjoint because they differ in which one tossed the first head here. So what does this thing look like? A1. Well, there's some number of tails. And that number of tails is even. And then the coin is in P1's hand. He tosses a head. Then there's some number of tails. And that is odd. And then the coin is back in P1's hand, and he tosses the winning coin. So this is for any k bigger than or is equal to 0, and any l bigger than or equal to 0. Right, that's what has to happen. If P1 tosses the first head, that means the number of tails before the first head is even. And if P1 wins, that means that the total number of tails is odd, which means that this in between the first and second is odd. And so this is what the event A1 looks like. Okay. Is that clear? Ish? All right, and the event A2, well, the difference there is which side is odd and which side is even. In A2, what happens is tails comes up an odd number of times. Then the second player tosses the coin that comes up heads, and then tails comes up an even number of times, and the first player tosses the winning coin that comes up heads. So we'll need to figure out this probability of A1 and this probability of A2. But before we do that, let's just see that we're going to get somewhere with this. So the probability of A is equal to the probability of A1, or A2, right? If A wins, it's one of these two cases that occurred. And these two cases are disjoint because in one case, the player 1 tossed the first head, and the second case, player 2 tossed the first head. So there's no overlap between these two sets, which means that that's just the probability of A1 plus the probability of A2. So we need to figure out these two probabilities, and then we'll be done. All right, so let's work at that. So the probability of A1. I've got a nice description of that set, A1. So we'll apply the definition. It's the sum over all the outcomes in A1 of the probability of that particular outcome. And what are these outcomes in A1? Well, there's an infinite number of K's and an infinite number of L's that define these things. So you give me any K from 0 to infinity, you give me any L from 0 to infinity, and I'm asking about the probability of this particular event, t to the 2kh, t to the 2l plus 1 h. So that's adding up all the probabilities of the individual events in A1. I get that by summing over all k and all l. So far, so good. So we better be really careful, not do anything fancy. Don't try inverting things or splitting here, because we're for sure going to make a mistake. Let's just do what we know. Okay, so I've got a probability of a very specific event here. What's in this event? 2k tails, followed by a head, followed by 2l plus 1 tails, followed by a head. So it's a specific sequence of coin tosses. So the probability of that thing, of course, is just the length of the sequence, right? The probability of getting these 2k tails is 1/2 to the 2k, then 1/2 for this thing, then 1/2 to the 2l plus 1 for these 2l plus 1 tails, then 1/2 for this thing. If I add all of that up, that's 1/2. I've got a 2k, I've got a 2l plus 3, because there's a head here, there's a head here, and there's an extra plus 1 up here. All right. So, the plus 3, of course, is, as usual, is annoying. But what does that mean? That just means that it's 1/2 to the 2k plus 2l times 1/2 to the third. So there's just this constant 1/8 sitting here. And this double sum is just a whole bunch of terms, but each one of them is multiplied by 1/8. So it is safe to pull that thing out front. So we'll put that out front. Still get the double sum. Half to the 2k plus 2l. All right, so now focus in just on the inner sum. L goes from 0 to infinity of 1/2 to the 2k plus 2L. Okay. The 2's are slightly annoying, but more annoying than that is this 2k in here. But if I just focus on this thing, this inner sum, then k is not changing, right? Think of this as two nested for loops. In the inner loop, the value of k doesn't change. So I can pull it out as long as I don't take it all the way outside the outer loop. So still got the 1/2 to the 3rd in front. I've got the sum, k equals 0 to infinity. But now I pull out the 1/2 to the 2k. And inside I've got the sum L equals 0 to infinity of 1/2 to the 2L. Okay, we did everything carefully. All right. What do we do about this 2 up here that's annoying us? Bring it in. 1/2 to the 2L is 1/2 squared to the L, which means this thing is really just 1/4 to the L. And finally, this thing on the inside, we know what it is. It's an infinite sum. There's a summation variable going from 0 to infinity. There's a constant x to the power of that summation variable. It's exactly the thing that we understand. So we've got 1/2 to the 3rd. K equals 0 to infinity of 1/2 to the 2k times, and what's in here? It's going to be 1 over 1 minus x. X is 1/4. And so this 1 minus 1/4 is 3/4. 1 over 3/4 is 4/3. And now I've got a big sum here where each term is multiplied by 4/3. So let's take that out front. Okay, good. Now what about this thing? Is this hard for us now? Nope. What is it? 4/3. So exactly what we did to deal with the sum over L. This is the same sum, right? It's 1/2 to the 2k. K goes from 0 to infinity. So this thing here is actually 4/3. So we get 4/3 squared, 1/2 cubed. All right, so what have we got? Let's go slowly. 16 over 9 times 1 over 8. 16 over 8 is 2. So that's 2 over 9. Now let's take a step back. Remember what we got really dug into this this computation. Is that the probability that player 1 wins? That's one case in which player 1 wins. There's still a second case. So always remember when you get really dug into some calculation like this and you finally get your answer, don't slap it down and say 2 9ths, because you'd be wrong because you forgot, oh, this was just one step. We still need to know probability of A2. Now life is easy because probability of A2 we still get a double sum. The things inside it are a bunch of tails, an odd k plus 1 times, then a head, then tails, an even number, 2L times, and then a head. But the point is that this is a very specific sequence of coin tosses, 2k plus 1 tails, 1 head, 2L tails, and 1 head. The only thing that matters is actually not the sequence, it's just the length of it. And we already figured out that that's 1/2 to the 2k plus 2L plus 3. And that's this thing, right? That's the same thing we've seen before. So now we skip a whole bunch of steps because we've done them already, and we get that that's 2/9. All right, and now we're done. Probability of A is the probability of A1 plus the probability of A2. We know the probability of A1 is 2/9, probability of A2 is 2/9, so we get 4/9. 4/9 is less than 1/2, so in this game, you don't want to be player 1. Player 2 has the advantage. Okay? That was not at all obvious from the outset. It really took some thinking. Now, unless you're really, really quick, if someone just asks you on the street, do you want to play this game with me? Do you want to be player 1 or player 2? It would be hard to, on the spot, say I want to be player 1 or player 2. Yeah?
In this game, be equal if determine who's first, also be introduced.
Yes, so if you toss a coin to decide who goes first, then that equalizes everything because, so basically everything is conditional on actually we'll see in 1 second why that's true. From something called the law of total probability, and we'll use it here so that maybe you could have figured this out more quickly using that. But for now, everyone is good with this? Yep.
So for the probability of player 1 winning player 2,
Yep.
that's equal to the probability of player 1 winning game 1 squared. Is that a coincidence or is that?
I think that's a coincidence. We'll see though that it is, you can express it as the probability of a product like that, but it's actually the sum of 2 products. Okay. So, all right. So now that we're happy with that, let's see how I could have saved us a whole bunch of time and done it differently. So there's something that the textbook calls the law of total probability. And it just says that if you give me 2 events, A and B, then the probability of A is equal to the probability of B times the probability of A given B plus the probability of not B times the probability of A given not B. So it's called a law because it's not even worthy of lemma or a theorem because it's immediate from the definition. Let's just look at this thing. Probability of B times the probability of A given B. Well, what's the probability of A given B? That's the probability of A and B divided by the probability of B. Oh, those cancel. What about this thing? Probability of not B times the probability of A given not B. Well, that's just A and not B divided by the probability of not B. But those two things cancel. So this is just the probability of A and B plus the probability of A and not B. And those are two disjoint sets. A and B and A and not B are disjoint sets. Together they're all of B. So this is just equal to the probability of A. That's all the law says. It says you can take something simple probability and make it complicated looking, but actually it's the same thing. So let's see how we could use that here. In particular, this probability that P1 wins game 1, this is equal to the probability that P1 tosses the first head. Right? So that's what it means to win game 1, is you toss the first head. So let's use now this law of total probability, and let's let B be the event P1 tosses the first head. So then I know that the probability that player 1 wins is the probability of B times the probability that player 1 wins given B plus the probability of not B times the probability that player 1 wins given not B. We know these four quantities already. So probability of B, that's the probability that player 1 tosses the first head. When analyzing the first game, we realized that that's 2/3. Now, the probability that player 1 wins given B. So the probability that player 1 wins given that they toss the first head. So the game is, you've played the game, player 1 tosses the first head, and now we're really playing the original game, right? The next head is going to win, except who goes first? It's player 2 now. Player 1 just tossed the first head, it's player 2's turn. He's the first player in the original game. So it's more likely now that player 2 is going to win, and it's the probability that player 1 wins now, because we're playing the first game, but with player 1 as the second player, is only going to be 1/3. So it's like, at this point, this is player 1 is the second player in the original game, or what we call game 1. Okay, probability of not B. So this is the probability that it's not player 1 who tosses the first head, but it's actually player 2 who tosses the first head. What's that probability? 1/3. We learned that when we analyzed the original game, because if player 2 doesn't toss the first head, or player 1 doesn't toss the first head, player 2 will. So that happens with probability of 1/3. So now we're looking at the situation where we've played the game for a while. Player 2 just tossed the first head. The coin is back in player 1's hand. That's the original game. That's game 1, right? Player 1 starts first. First head is going to win. So that's 2/3. And look at that. That's 2/9 plus 2/9 is 4/9. So this really boring-looking thing, this complicated-looking thing that seems to only complicate matters, actually, in this case, made life really easy for us. So sometimes this conditioning on something happening, splitting it into the event B happens or it doesn't happen, it sometimes makes these two things somehow easier to deal with by themselves. And now going back to your question about if you toss a coin beforehand to decide who goes first, then the event B can be the coin comes up heads. So you'll get something like 1/2 times some probability. I don't know, I don't even care what it is. I don't even care what the game is at this point. But it's the probability that player 1, the first player wins the game, plus 1/2 times some other probability, which is the inverse probability. And if you add those together, of course, you get 1/2. So the way to make any game fair, if you're worried about this, is you first toss a coin to decide who goes first. Then you'll know that it doesn't matter what the rules of the game are. If it's just a game of chance, then each player is equally likely to win. Although, it can somehow take a boring game and at least make it fair, right? I mean, this is true even when p equals 1. So maybe the game is like really boring. First player always wins, in which case tossing the coin is really the only interesting thing that happens in the whole game. Okay, so let's leave it at there for today.